Hi gang, I just wanted to do a quick intro because in the video I mentioned this structure here. This is a prime sieve, prime like prime numbers, P-R-I-M-E, and then another word, S-I-E-V-E. Do a search, check it out. It's really cool. It's a graphic representation of mathematical constraints, and that's kind of what I'm doing here in my next video, which this program could easily be adapted to a game. So give it a check and let me know what you think in the comments below. Thanks for watching. Hi gang, Mr. Ed here for another episode of Mr. Ed Makes, and in this episode I'll be playing around with Applesoft Basic again. And I wanted to show you this program because it deals with a couple things that I discovered early on when I was programming. And I also like the way that this kind of generates patterns and what it's really doing overall. So when I first wrote the basic program, let me pull it up here for you. Shut that off there. Okay. When I first started this program, it's actually overall it's not very long. Pretty short program. Let me roll that back down. When I first wrote it, it had 8 lines, and it only had one snake, and it wasn't a snake. It was just a square that went down. It didn't leave its path like it does here. It leaves its path for 2 reasons now, because I want to see the path it took, and because it saves time, because erasing its path takes up processing time and it just slows the program down. But you can see here it has an array for the different snakes, and it runs through. Right, this is really sloppy code. There's actually a lot more going on here that I'm not doing right now. Some of the things are deactivated because they won't run together. For instance, I can have more than 3 snakes, but when I do, I don't get the horse race at the bottom. It'll cause an error. So in order for me to have the horse race, just because there's limited display area at the bottom, I'm limited it to three snakes, but it can go all the way up to 20. But when it does, I have to take out that part of the subroutine so that it doesn't throw an error. So it just stops displaying them. I could hard code that in there, but it's just easy for me to rem it out as to hard code. And plus, if I hard code it, it's going to just take up more time in the processing. So let me go back to the program here and I'll show you what's going on. All right, let me stop this here. Let me run it and stop it real fast so you guys can get an idea. So it's a very basic program. I print a bunch of lines and they alternate, so they basically become floors or levels, and the snakes are falling or traveling through each level where there are gaps for it to go until it gets to the bottom. Now a snake, you'll see down here at the very bottom there's these numbers 2, 4, and 4. Well, this is snake 1, snake 2, and snake 3. And snake 2 has a 1 in 2 chance of deciding to skip over a space that it can go down. Instead of going down that space, it may decide to just jump over that and go to the next one. And this one, the next one's 1 and 4, and 1 and 4. And there's factors of this propensity to jump, and it's randomly determined. And this kind of gives me that variability that I need in the random numbers. Otherwise, if you run equally constrained random numbers against one another to see which one will occur the most, you're going to fail. That's just how random numbers are distributed. You have a percentage chance of whatever constrained number coming out. Unless you make adjustments to that, you're always going to have like an even stack of random numbers. I don't know if that makes any sense, but I wanted to eliminate that because I don't want it to be an even horse race every time. And that's what I have going on down here, and I'll show you that. But first let me explain that every time a snake makes it to the bottom, it counts as a lap, and then it restarts at the top. And each lap will move a marker over in this display area, and that represents where it's at in this horse race, I call it in my brain. And because it can make choices to jump over spaces, it may happen upon a quicker route through. So it may be in position 1 for the first lap, but it could lose that position because it may just through random occurrence select a longer path through this maze, if you will, than its competitors, and it will lose its lead. And this can waver back and forth dramatically throughout the course of the race, which is like 39 laps, something like that, which is actually the distance in printable spaces between here and there. All right, let me run this. So I make my my floor, and the snakes go through, and they ignore their own path. They'll just go down. If there's a path in that gap, they'll just go down in it and over, and you can see where they terminate. It's different spots. Sometimes it's the same, sometimes it's different. And then down here, these lines represent where it is. So here's the interesting thing about this set of random constraints. If it has a 1 in 2 chance of skipping over a hole, it's going to more frequently ignore a movement downward in favor of going so many movements to the left or right and then finding another spot down. This costs it time and steps. And that's represented in a ratio between the lead ones, who should be pretty much neck and neck because they each have the same propensity to skip over a hole, which is 1 in 4. So it's not very frequent. So they're just going to keep falling. They see a hole, they go down, see a hole, they go down. They're not going to mess with jumping over to find a quicker way, because we can see here it just takes longer. And the distance between their lead is a ratio that's represented in these values here too. So you can see, even though they're random numbers, there's pretty much a random way it goes through this maze. The results over time of that randomness describes a bell curve. It describes a predictable set of numbers, and we can actually see that ratio represented there. Now here we have a new, once the race is over, it starts again, and we get new propensity values. Here, 1 in 6 chance it'll jump, 1 in 4, 1 in 4. And we should see, as course we are as predicted, the 1 in 6 chance of jumping over a hole. I consider those distractions. If it gets afraid to jump or to go down into a hole, jumps over it, I call it a distraction. So this one is less distracted. 1 in 6 chance of distraction, while these have a 1 in 4 chance of distraction, which is going to cost them time in the race. And we can see the distance between their speeds, or the steps they take, grows, and it's a pretty even ratio. Sometimes it falls out of kilter, but this is just 1 or 2 samples of a race. If you take those samples over and over again, Bayes' theorem tells us that the odds will be more accurately represented. So we're getting to the end of this race here, and I also want to describe something else that's going on here that can affect the outcome in an inverse way. Sorry. Okay, every time a new maze is built, the density of holes to floor is random, and there can be fewer holes or there can be more. And the interesting thing occurs when there's more holes, there are more opportunities to find quicker paths, and those can be discovered by being more distracted. In essence, if you have a greater density of holes, then the distractions don't add up as much, because there's more opportunity for a distraction to become less of a cost in terms of the number of steps that need to be taken in order to find the next hole. So you can kind of get this the strange skewing of the outcomes based on the density of a floor to holes. Well, what statistics can do is it can actually work out that difference and come up with the same probable outcome. And this is done through standard deviation, and it's done in statistics a lot to rule out things like factors that can influence the outcomes of random numbers. And this model kind of demonstrates that in a very graphic way. And I kind of like that about art, about looking at things visually and getting a sense of what may be going on. And this is just one of those ways. Now, the patterns that emerge are really interesting too, but they're kind of like a prime sieve. It's not like a real thing per se, but it does emerge out of the random constraints or out of the mathematical constraints in the system. You'll always see pretty even ratios. If I counted all of the blocks of colors and divided them up and added them up, I would see that they're pretty even in relation to their propensities down here. Once I take out all of the deviating factors, I'll come up with a pretty even set of numbers. So that's a simple program that can kind of describe distributions and how random numbers accumulate and make a curve sometimes. Sometimes it's just an even plane of random numbers because they all have the same chance of coming up. And I like the patterns that it makes. I was working on one yesterday where it would try to find the fastest way down. And I came up with this interesting problem. If you simply look at the floor you're on and go to the nearest hole, that only works for that floor. It could cause you to be further distance away from the hole on the next floor. So in order to efficiently find the quickest route through, I would have to go through the maze. I couldn't just look and see which hole is closest and then go through that one and then perform that operation for each floor you go down, because it's not going to win. The best way to do it, I think, would be to set up a neural network, and if you have to have the same floor. Of course, you can't randomize the floor. I think you might be able to. I don't know. I couldn't. But you could set it up to where it keeps track of how many steps it took to get through the floor, and it just basically averages those out and finds the winning occurrences as it goes through. That may not make any sense. I'm not very good at explaining it, apparently. Probably because I don't completely understand it. This is something that I'm still trying to understand, is how to do neural networks and program them in. I can kind of understand how you can get the constraints to be realized, but I don't have the programming strength to do it. So maybe maybe one day I'll figure it out. But anyway, I did figure this out. It's got a couple glitchy things in there that I wish I could do better, but because I didn't start out with this idea, this full idea, it just kind of evolved as I was writing the program. It's not written the best way. I had to go back through and refactor some of my variables, and that was sloppy. And so, if I get a thumbs down for this, I completely understand. I usually get thumbs down for my programming because people, they see it, maybe they expect more. I'm just a hobbyist. I've only had maybe a semester of computer programming formally in college, and I had 2 or 3 years of it in high school. 1 year was independent course study. I basically taught myself because there weren't any teachers that could teach me, because it was a small school, didn't have the best staff. They basically, learned as much as I did pretty quickly. 2 years to do that at that time, in the early 80s. But the point is that it's not going to be the best. But it does show ways of doing things, and if you're keen, you can figure out on your own. You can kind of extrapolate and maybe improve, and I certainly welcome that. And this is just provided as inspiration to get out there and just play with things, play with code, and see what you can come up with. You could get some amazing insights into a lot of things around you that you may not have gathered any other way. So I encourage you to do that, and I do appreciate you watching this episode of Mr. Ed Makes. And until next time, you guys, take care.